Welcome to our wing design video. The design process involves sketching, Excel, CAD modeling and simulating, and building and testing. First, we came up with some sketches to understand the internal structure of the wing. Then we sketched spar cross sections to test in Excel. We tested the spars that passed the test in Solidworks and repeated these tests in the lab to investigate further. The point load applied is the load factor times mass times G all over 2. Bending moment occurs in the wing due to the lift. Maximum bending occurs at the root of the wing, and maximum deflection occurs at the tip. The following 4 spar designs are box designs we have tested in the lab. Excel shows us that for the different spars, they theoretically should fail around the same following dimensions. This was evident in our testing as the 44x44 mm box design failed by compression. The box beams were most similar to our Solidworks models, could withstand much more than 20 newtons, so it was not suitable. This may be due to an excess use of hot glue, causing a spar to be much more elastic than supposed to be. Torsion occurs due to unequal load distribution at half chord point. The wing must have torsional compliance to be capable of flight, which is here is 3 degrees. Loose joints, as seen here, cause extreme twisting, but not suitable for flight, and a folded spar design prevents this. To minimize twist angle, we designed beams with mass concentrated to neutral axes because equal of torsion is semi-span divided by the shear modulus times the polar moment of area. Because bending moment is equal to the load times the span minus the distance from the root. As distance increases, the bending moment decreases. Therefore, to minimize spar mass, taper the spar. Bending moment may be too large for certain parts. The wedge design was best as stress was highest at the tip and least likely to fail from compression at the root. It was theoretically supposed to fail closest to UTS of foam board under 20 newtons force. Using the information we have gathered from testing the non-optimized bar we drew from final sketches for a non-optimized wing, which we plan to actually assemble. The wing passed test in Solidworks with deflection of 2.3 mm and a twist angle of 1.1 degrees. The max stress was 6.119 megapascals and the stress was distributed evenly across the wing. Due to our testing and research, we found that the model in Solidworks passed the test easily, though we know that as the distance increases, the bending moment decreases. Therefore, we went on to design an optimized wing. So here you can see that we chose the wedge for the final optimized wing design, as it was simple to assemble and was a strong design. We could keep the airfoil the same size whilst reducing the mass along the wing. The model also passed tests in Solidworks with displacement of 2.8 and a twist angle of 2.4. In conclusion, we have learned how to follow the design process. It's vital to sketch or plan out first and do calculations and do CAD, although not everything translates to reality due to changing variables.